Dr. Niklaus Veta. Niklaus is representing our Institute Director this morning, and just for welcoming our participants and saying a few words for us. Niklaus, thank you very much for joining. Niklaus is representing our Institute Director this morning.
We do have some echo here.
Just for welcoming our participants and saying a few words for us. I hear you, Niklaus.
Yes. Okay, thank you very much, Fabio. I'm very glad to be here. I would like I wish a very warm welcome to all the participants to this CINE workshop for fuel cells and methane to product conversion. When I hear these words, methane conversion, fuel cells, I immediately think about global warming. I think about cutting edge technology. I'm thinking about taking care of the environment, taking care of our emissions. And obviously, we cannot take care of people without taking care of our emissions. And this taking care of people is well within the mission of our institute. Nuclear energy, which is the main research area at IPEN, is also carbon-free and has recently received a lot of renewed attention as an alternative. Also, our research on radiopharmaceutical products is another example on how to help people. So it is of great importance to see and to have such initiatives as this CINE workshop. And these initiatives, they are connected and serve to increase the quality of life. It is science serving humanity to decrease the problems of humanity and to increase its well-being. Science for the conservation of our planet. All these objectives are part of the goals for sustainable developments that were established by the UN, and also the net zero for 2050, which is an international scientific consensus. So we will not achieve these goals without new technologies for decarbonization and without completing this cycle of a worldwide transition to carbon-free energies. So I'm very glad that this is happening at our institute. And without further delay, I would like to thank you all for your presence, and I wish you all a very successful workshop. Thank you very much.
Thank you, Niklaus. Thank you very much for joining us and for all the support that IPEN is giving to our program here. Thank you very much. So without any further ado, I would like just to two options for questions today and tomorrow. Here, if you're here in the seminar room, you can raise your hands. We're going to handle the microphone. If you're online with us, you can either use the virtual hand or maybe the chat function, and we'll address your questions. For those of you that are more comfortable, you can shoot your questions in Portuguese. We have no problem in translate them, or just let us know. Let's try to make it this presentation and this workshop as engaging as possible for everybody, presenters and the audience. And I would like to start today, this morning. It's my pleasure to have here Dr. Ernesto Pereira. Ernesto is an old friend of our group here. And it's a pleasure to have you here giving you the opening talk of our workshop. Ernesto is a full professor at the Universidade Federal de São Carlos. He's a CNPq, our National Research Council research fellow, 1A level, toppest, highest level, and will be sure giving us a lot of information and interesting, telling us a little bit about your research. Ernesto, thank you very much for coming.
Thank you for invitation. Today I will talk about my recent result, and this is interesting for me because I think that this is the first time I'm talking at the place. I got some talks before, but you know, all of them were made remotely using the computer. This is the first time after the pandemic situation that we had. And also, I'm a material scientist. I had been a material scientist for about 40 years right now. But I changed a little bit in the last few years because from a point of view of to go deep in the understanding of the system that I like to study, the solid state is too much complex. And as all of you knows, a material is not only the composition, it's the composition, the doping, the grain size, and the surface state. Everything has an important consequence on the properties. And I think that 5 years ago, I knew the flux batteries. Flux batteries are all of the system in a solution. The electrode is not an electrode anymore, it's a current collector, just this. And at that time, I decided to change a little bit and to start to investigate the ions in the solution. And the electrochemical system is another thing that I like too much to study in the solution. And as I told Betty a few minutes ago, the difference is that now the theory works. And the solid state, all the electrochemical that I know is just an approximation, a law of quality approximation to describe the system, to describe the reaction, to describe how the reaction front go inside the solid state. It's not easy. It's not easy. And besides that, I like too much to use low-cost techniques to investigate system. And one of the cheapest system, tools that we had now is the computer. Everyone use and have and got and make the data. But I like to use the computer for chemometrics. I like to use the computer for simulation, for finite element simulations. I like to use the computer for image data analysis. And this is enthusiastically because most of these I can made using, it's not a personal computer, but it's a low-cost computer, about 20,000 reais. I have computers in which we can make several calculations. For sure, I had problems before because I investigated the system and I got so much data sets and so huge that in this case, I don't have the computer to analyze, and they are just stored in a hard disk waiting for the computer. It's that possible to point? Yeah. One of the systems that I like too much to investigate, because this is an old one, and when I was a young child, I made this experiment in a science work. Water splitting. This is an old problem. And actually, I did not use new methods. I use low-cost methods to investigate. From my point of view, these are the challenges of the 2021 century. The main problem is the energy. Actually, I don't think that the energy itself is the problem. I think that the energy waste is the problem. What do you mean about energy waste? Think about a car. As some of you know, the yield in the car for the gas consumption is about 20%. But the car weighs 10 times myself. Then I need to divide this by 10. And in this case, just 2% of the car carries myself wherever I want to go. This is the problem. For each 100 liters that you put as gasoline in your fuel tank, only 2 of them, 2 liters, carries you where you want to go. This is the problem. The energy waste is the main problem. You can think like this. We have here air conditioning, yes, there. And why not to change how we build the buildings? For example, I read something about to make heat exchange under the ground, because the temperature under the ground cools too fast as you go deep and deep. And this is an efficiency way to maintain the ambient temperature at low levels. So my point is we need to talk more about energy efficiency together with new materials to make the efficiency high. This is water splitting. We can do it. We have the bubbles formation. This is a very complex system because we have the bubble formation. And in this case, we are talking about a photoelectrochemistry, a photoelectro reaction. Although most of my work, I don't put yet the light. It's too complex, just like this. Hydrogen, water give oxidation, give high oxygen, and reduction give hydrogen, and bubbles detach from the surface. As I told you, in the case of the electrochemical water splitting, we have the electric field, but we need to talk about the mass transport inside the solution, the bubble dissolution into the solution, the bubble transport across the solution, which leads us to we must care about the fluid flow in the solution. I will show you something about this kind of effect. Again, one important stuff that we are investigating in my lab is that as in the electrochemical system, the whole reaction occurs at the interface. We ask to ourselves that if the pH values in the bulk solution is the same as the interface one. And we start this work for sure. We start this work thinking about a specific reaction, investigate the electric deposition of metals in acidic solution, and we got hydroxides. This is the starting point that I think that pH change was important. But in the case of water splitting, it's also important. This initial work, we are talking about a simulation. The boundary conditions and the equations that we have into account. We are talking about the pH at the interface and how it changes as the as the applied potential is swept from one value to another one. As we can see, if we start the reaction at a pH value of 3, we can observe a change up to 8. It depends also if you are talking about different materials, because the mechanism of the hydrogen formation change. Both are Vollmer-Tafel or Vollmerovsky. In the case of Vollmerovsky, the pH change is much more important than in the case of Vollmer-Tafel. This is the difference is that you have the high mobility of hydrogen atoms over the surface. And in the case that we don't have the high mobility case, we have the pH change interfacial change important. Then we start to investigate what we can do to inhibit this pH change. Let me tell you, the problem with the pH change is that you develop a new material for acidic solution, but really you are working at the interface in alkaline pH values. And then your electrode just leaks into the solution. Then we start to investigate what can we do? And we propose at the beginning to use a step with an off time, not continuous current value, but like this: start, stop, start, stop. Then we give to the system a time to the transport of the excess of hydroxyl ions from the interface into the bulk solution. And actually, for sure, we use different conditions. We stood the frequency, we stood the difference of T on is that time where the current is on over the total time of one square wave and the initial bulk pH. And what we got, starting at pH 3, using different conditions, we observe like this. This is the beginning, pH 3. And as you make the square wave perturbation to the system, a current one, we have a transition in this case. In a second situation, you always has the peak in a different pH, in a different range. In alkaline pH, we start in acidic one, but we don't have the transition. These are the current that we got, the current waveform that we use in the system. And for sure, I told you, this is simulation data. And then for sure, we start to investigate this using experimental data. They are very simple to perform in an electrochemical cell. But until now, we can't find a situation where even this spark here does not occur experimentally. And I think this is very important because beside the electrode stability, there is an energy loss when you have this pH transition. You have, it's not a new, but you have an increase in the overpotential of the cell due to the interfacial pH change. Then, to measure this pH change, we built this ring where we measure the pH, disk, any material you want to investigate. We prepare a new pH electrodes using, in this case, an ink. We use the Pittini method to prepare a region oxide over the system. And then we can build a ring disk electrode to measure the pH. And this is the pH method. And what we got, we can have this is the added value at different current rotation, and these are the potential, open circuit potential as function of pH, and we have almost linear slope here. This was only possible because for a long time we work with Pitini method. It's this solution wet method to prepare materials, and also this is the film that we painted over the glass to prepare the electrode. But actually, I like to map this work because at the beginning, this was the starting point to prepare different pH electrodes. Is the micro one, the micro electrode. As you can see here, we prepare a whole pH electrode, which you know, this is a complete electrochemical cell. It's not only an electrode inside a needle, which can be used for anything you want for different applications. The reason that I prepared these electrodes was because one student from a different lab came to me and asked to measure the pH of a drop where she has some kind of protein inside the drop. And if she use a conventional pH electrode, she will lose the protein that she needs to investigate. But one subject that we are working are the interfacial pH chain, both experimentally and computational. And the other ones are the bubble evolution during water splitting. We investigate very different experimental situations, and we built this system, and we use a cell phone as the camera with a lens, a special lens to make this system larger. I think that we can see they are small films. Could you? And the other one also. We investigate everything that we got here. We investigated the bubble formation. We investigated the large bubble, the small bubble, the different ratio among these ones. In this case, we are working in acidic solution. And the next one, please. Eu vou tentar aqui. These bubbles, the morphology of bubbles are very different from experimental condition to another one. If you change the current, the applied current, it changes. If you change the pH value of the solution, the morphology of bubbles change. If you change the electrode material, it's changed again. If you change the roughness of the electrode, it's changed one more time. What I'm asking to myself is why it changed. what are the properties, the fundamental properties of the electrode, the system, the solution, which leads to the exact moment that one bubble detaches. A second question, why we have two bubble size distribution? As you know, this is from my point of view. The first thing is to have reproducible data. Then we count it. Then we analyze the system, propose a model. And then, in sometimes, we can also make now, as the fourth step, an improvement of any property that you want to in the system that you have now investigated. And this is what we are at this moment to investigate. We method to automatically count the data, count the bubbles, the bubble size, how much time it. The previous one, please. If is that possible. Yeah. Now, please, can we try again? Acidic media and alkaline one. The same current. As you can see, in this case, we don't have these large bubbles. The reason is that we have the saponification properties of the alkaline solution, perhaps. But I'm very interested in to know what is the fundamental property, the next one now. This is the problem. This is the problem. Sorry? So now we know that. Just open again. Why am I interested in the bubble formation? This is because when you have a bubble growing on the surface, under the bubble, there is no reaction. This is a poison for the electrode surface. And as you can see, you have rounded bubbles at the same time over the surface. Then you have an effect of decrease the number of active sites over the surface, and for sure this is also a loss of efficiency of the system, and that also leads to an increase in the overpotential. I suggest you not to make a presentation, to just this one. As I told you at this moment, we are just counting the bubbles over different conditions. As you can see here, we have different in the distribution of the size. Depending if you are talking about hydrogen bubbles or oxygen bubble, the properties, the morphology of the bubbles are different. The next one, please. These are different conditions now in alkaline media. The previous one was in acidic media. The next one, please. The bubble growth over the surface. These points are the point that they detach from the surface, and then we have the mean size depending on the current density. The next one, please. We followed also just the properties of large bubble. The next one, please. And finally, the morphology of small bubbles and large bubbles are different, and I'm also interested to understand how is the ratio between the volumes of large bubble and the small bubbles. As the time goes by, as you can see, you have sparks. We don't know what this means at this moment, but it's very interesting that we have it and now not like this. This is more flat behavior, and this we have several sparks in the system. The next one. We also made histograms. This is interesting for me because we have a log normal distribution, which is the same when we study the grain size distribution from the solid state material, polycrystalline solid state materials. And I was not expecting that we have the same kind of behavior. In this case, it's not clear, but in the other case that we count a large number of bubbles, it's very clear that we have a log normal distribution. Next one, please. And also, we observe like this in some conditions, not all the conditions. Instead of the bubbles just go upside, they go in diagonal. And I remember the wedding dress. We are talking this, we are calling this wedding dress effect. On the next one, please. We have another film here, if that's possible to present. And first we count the effect. And after that, we start to build a model to describe it. And it was surprised that the model, considering this kind of effect, we can describe, and then in this case, we can propose that what we are seeing right here is an effect of the convection, of a natural convection that goes into the solution. This convection in the solution there leads to an important consequence over, which is the covering of different bubbles. The next one. This is the last one. Then we built a model to describe it. The next one. And the advantage to build a model is that I can test many dozens of different conditions computationally, comparing to experimental behavior. The next one. And then we disclose, we investigate like this. These are just computational experiment, and we observe a different covering of bubbles into the surface due to this convection into the solution. This is very interesting. Now we know that if we had an electrode, in the center of the electrode, we have a large amount of bubbles compared to the edge of the electrode. And again, we have an increase in the overpotential, which in this case is not constant. It's the position over there. The next one. For different conditions, the covering at the center, the surface area, as you can see here, the amount of bubbles in the center is always different from the edge, the average value higher for the center. And this is the last work that I want to show you. This is a computational simulation experiment data set. And for sure, this is not an electrolyzer. This is an electrolyzer. Then we start to ask what happens in a large one, electrolyzer, vertical one, when I have all of them, we have bubbles, but the bubbles from the bottom side, they go through the surface up to the upside. And what we got, we investigate this. And what we got is that the local current, it's position dependent also, but in this case, over the surface. So realize that. Now, we know that if you have a large electrode, the local conditions, the local currents at a different point of the electrodes are completely different. Like this one, for sure, it depends on the current values. For commercial, those current values which are using commercial electrolyzers, this for sure occurs. The effect on the energy, as you can see here, it depends of a lot of different stuffs. We can step this last film. Want to? Now you know how. Tinha. No, that's no problem at all. So this is, please, the next one, please. For the next one. The next one. No, this one. The conclusions that we have until now are just partial conclusions for sure. But I think that the important point here is that we use low cost, both experimentally and computational experiment data acquisition to investigate the different is, for example, there's a large number of papers in the literature which investigate the bubble formation and growth, but they don't stay every time they study just one bubble. And now what we are doing is to investigate all the bubbles and the bubble size distribution over the surface, which lead us to gain new insights about the reaction. Next one. These are pre-pandemic group. Myself, Professor Lucia, Professor Elton, and the students. This is a different one. This guy is undercover right here. And feel deep in the past, 2013. And 1996, you were there. And this last one with the dinosaurs, Ronaldo, Lúcia, eu, myself, Beth Santiago, Paulo Livi, Carla Eiras, Inês Tomita, and Valeria, all of us, we worked with the same person, Professor Luis. Thank you very much.
Thank you very much, Ernesto, for this very interesting presentation. I got here in the spot to be caught on the camera eye. And well, we are open for questions locally and abroad here. So that's one of the challenges of making this as an adventure, making a hybrid event. So we cannot be in control of everything. So I need the people online, our host and co-host of the Zoom session, to tell me and pass on the questions that we may have online. And here, you guys just feel free to raise your hands and we hand over the microphone to you. Please go ahead. Don't be shy. There's no. Okay, André.
Very nice talk, Ernesto. I was curious if you have already any results comparing electrodes with different morphology, different roughness or something, or different grain size, things like that. That probably can affect the bubble morphology as well.
For sure. I think you are right. And I think that one of the main points that we deserve to investigate is the wettability of the surface. At this moment, we just finished the automatic data treatment to get the information, the quantitative information from the image. And the next one is to first the roughness, which we are starting right now. And the next one after that is to check for this high technology electrode materials for this application.
Danielle. Oh, that's high tech. Hey, Cauê. Good morning.
Hi, Fabio. Hi, Ernesto. Very nice presentation. Do you hear me clearly?
Very good.
Okay, perfect. Ernesto, congrats for the nice presentation. I wonder to understand how much can we extend these nice results you have had about the bubble formation for both sides of the electrolyzer. I mean, we have the same effect that you have investigated for the hydrogen production and for the oxygen production. How much the nature of the diluted gas influences on this bubble evolution? And meanwhile, I would like to make another question for you too. How much can we extend these results for CO2 reduction in terms of bubble production?
The first question first, then we'll talk about the second one. I show you some results that hydrogen and oxygen are different, leads to different bubble morphology. Besides the bubble morphology, the solubility of these two gases are different into the solution. So the chemical composition of the gas, any gas, they are important in this case. We detected this. And about CO2 reduction or about any gas formation or any
Hello, Cauê. Do you hear me?
Hello, Daniel, back. I believe that the connection has broken there because I didn't hear from the CO2, the reply about the CO2 reduction. We didn't hear.
Can I continue, Cauê?
Yeah, please.
Listen to me.
Yeah, now I am. Yeah, the last part that we have heard is your introduction about the CO2 reduction. Could you come back there?
There is a strong difference in the solubility of CO2 from acidic pH 5 to alkaline pH 10. It's about 10,000 times. It's too much. And now, as we can talk also about time-dependent pH values near the surface, then we intend to use this both information to increase the solubility of CO2, starting in acidic, but we have also together with the reduction of CO2, the reduction of hydrogen, and then the formation of hydroxyl ions. And we suppose that we have a new force to transport the CO from the book to the interface. We made some simulations until now, and the results are promising.
Thank you.
In the case
I think that we need to talk more this in person. We need to talk more this in person because this is something that really interests me a lot. Thank you very much.
You're welcome.
Any other questions? Still have time for one last one. I don't know. Danielle, please keep me posted if you have people online with questions. If not, Ernesto, did you notice? I mean, all those bubble release, they are responsible for a well-known phenomena in high-temperature electrolyzers, which is basically cathode spallation. So at the end of the day, we have a microstructural damage related to those bubble release. Do you guys look at that kind of effect of microstructural change of your electrode due to the bubble release?
In this case, we are talking, with platinum electrodes. At this moment, no, we are talking nothing about this. Our effort right now is to have a complete counting of all the bubbles that we have in the surface. But for sure, there are many phenomena which must be investigated in this kind of approach. As I told you in the beginning, the energy waste is the problem. We need to decrease the overpotential. For sure, we need to have stable electrodes. Yes, but water evolution, it has about 50% of energy efficiency. And if all the hydrogen in the world was produced by electrochemical form, this cost about $70 billion in energy. In energy, the cost of the energy is $70 billion if all were produced electrochemically. And in this case, if you are talking about to go from 5 to 55, we are talking about 3.5 billion. This is real money.
Indeed. Okay. So thank you very much, Ernesto. Thank you very much. So now we start moving to our local presentations here. I think the next one is Artur, right, Artur? If you please come over. O do meio é o laser. Isso. Não é o do meio. Laser, exatamente. Deixa eu abrir o seu aqui. É esse aqui, né? Agora só espera um pouquinho e você vai aparecer, vai se ver na câmera lá. Tá vendo? É esse aqui, tá vendo? Esse também. Não, para a direita. Oi? Espera aí, agora. Pronto. Okay, Arthur.
Good morning, everyone. First of all, I'd like to thank everyone for coming and for the opportunity to present my work today. My name is Arthur. I'm a master student at Nuclear and Energy Research Institute. And for the past 2 years, I have been working on Project 11 of Methane to Product CINE division, where we are researching photocatalytic materials for methane conversion into add-value chemicals. Today, I'm going to show you some nice achievements that we found around zinc oxide-based photocatalysts with its surface modified by palladium nanoparticles deposition. First, a little bit of contextualization. The methane conversion studies has been increasingly the focus of research given the carbon reduction policies adopted by society. But converting methane is as beneficial as it is challenging. The methane have a highly stable and symmetric molecule, as you can see, and converting it requires a large amount of energy. This energy is conventionally given by severe conditions of temperature and pressure, but studies of the past decade have shown that those thermochemical methods for methane conversion are only viable for hydrogen synthesis via methane steam reforming. Otherwise, the severe conditions tends to disfavor the reactions to occur. Some of those reactions are presented here at table 1, and we have some reactions of non-oxidative coupling of methane and aromatization to methane to higher hydrocarbon chains. But the coke formation is favored in here, and it leads to the catalyst deactivation that are needed for these reactions to occur. We have the oxidative process, like the partial oxidation of methane and the oxidative coupling of methane. But at those reactions, the total oxidation is thermodynamically favored, as we can see by its Gibbs energy. So these processes are of hard control, and we have low yields and selectivities. We have then the photocatalysis. The photocatalytic process is an alternative for methane conversion under mild conditions. The photocatalysis is based on semiconductors activation via UV light. And this way we can generate charges that can promote methyl radicals formation. In here, figure 3, we can see a scheme of the semiconductor activation. We first start in here with the irradiation of the semiconductor. Its energy have to be equals to or higher than the energy associated with the gap between the valence and conduction band of the semiconductor. When absorbing the light photon, electron can jump from valence to the conduction band, thus producing a free electron and a free hole of positive charge character that can react. We have then 4 major processes that can happen. We have processes A and B, suggesting the recombination of those charges at the surface or at the volume of the semiconductors, respectively. And more interesting, we have the processes C and D, where these charges can travel to the surface of the semiconductor's particle and be free to react with species present in the system. Talking about the chosen semiconductor, we have zinc oxide, and it is a common photocatalyst given its similarity with titanium dioxide, that is the base material for photocatalytic studies. Some of its properties that are favorable for photocatalysis, its polar structure that can promote charge separation and transportation along the semiconductor particle. We have a wide absorption band and a rich defective surface that can promote more surface reactions to occur. And besides that, we have the palladium nanoparticles deposition that can act as a co-catalyst. At figure 5, we have here the palladium nanoparticles deposit in the surface of zinc oxide. And a Schottky barrier is between the interface between methyl and semiconductor can trap electrons in the nanoparticles and prevent their recombination, the photogenerated charges recombination. At equations 1 to 9, we have some possible reactions that we expect in the system, like the semiconductors activation at line 1, the water splitting, the methane activation itself, and some coupling reactions. Besides that, we have some other reactions that might happen. And as experimental, we use two different methods for the photocatalyst synthesis. The alcohol reduction method, represented at figure 6, and the sodium borohydride reduction method, represented at figure 7. At both methods, we use sigma Aldrich nanosite zinc oxide as semiconductor, and a solution of tetrachloropalladate as a palladium precursor. Both methods were carried out in an aqueous system, and the solid content was separated by centrifugation, washed several times, dried in the oven, and grounded to a powdery appearance. As characterizations techniques, we first have the wavelength dispersive X-ray fluorescence spectrometry. We carried out this technique in order to determine the composition of the synthesized materials and the palladium containing in the samples. Given the low content of metal in the samples, we built a calibration curve that is presented at figure 8. And at table 2, we have the obtained results of the palladium containing in the samples, and they are close to the nominal, confirming the presence of palladium in the samples. We have then the X-ray diffraction spectrometry analysis, and the diffractogram patterns can be seen at figure 9. The expected peaks related to the palladium nanoparticles at theta equals to 40, 46, and 68 were not identified, given the low content of metal in the samples. Besides that, the nano-size appearance of the palladium particles can also broaden the diffractogram peaks related to the palladium nanoparticles, and thus they get lost in the background. Otherwise, we could identify the zinc oxide structure as Xrds, and it is represented at figure 10, and it's card at crystallography open database. We have then the diffuse reflectance UV visible spectroscopy. The obtained spectra are at figure 11. And here we first can see that zinc oxide activation occurs around 380 nanometers of UV light in here. And the palladium containing samples, we have some perturbation in the range of visible. But this data was treated with Kuehl-Bellman function in order to relate the obtained reflectance into absorbance to powdery appearance samples. This way, we use Talc method, represented at figure 12, in order to estimate the band gap of the materials. Table 3, we have the obtained results, and no difference between pure zinc oxide and the palladium containing samples could be observed. And it happens given particles are only the surface of zinc oxide, and no structural change is happening with the deposition, and no structural change in the zinc oxide. So the band gap is the same. Here we have some transmission electron microscopy images. First, figure 13, images of the pure zinc oxide. And we can see that no uniform morphology around the particles. We have some spherical particles in here, some rod particles, but no uniformity. At their sizes too, we have particles in the range of 20 to 300 nanometers. So this is not a homogeneous sample. In here, we have the palladium containing samples. Those black dots in here and here are related to the palladium in the samples. At figure 14, we have the alcohol reduction method samples. And at figure 15, the borohydride reduction method samples. And we see a difference in the size of the samples and in the agglomeration of them over the zinc oxide surface. Here we have some more images that we see with more clarity, the difference in the agglomeration and the size of the particles. In the alcohol reduction method, we have particles in the size range of 4 to 5 nanometers, and at borohydride samples, particles in 1.5 to 3 nanometers. As activity measurements, we use a photoreactor that is represented here at figure 18. And at the test, 75 milligrams of photocatalysts were dispersed into 250 milliliters of ultra-pure water. Methane was bubbled in the system in a flow of 25 milliliters per minute. And as light source, we use a high pressure mercury lamp. And we can see here at figure 19, the used photocatalytic system. As analytical measurements, we use mass spectrometry in order to identify the formed products, and the gas chromatography so we can quantitate the formed products. Feed detector was used to quantitate most of the products, and a TCD so we can see if we have some hydrogen formation during the tests. And we have a total of 12 injections in a total 33 minutes each, in a total of seven hours of photoactivity measurements. The first 2 injections, the light was off. At injections 4 to 10, the light was on. And at the last 2 injections, the light was turned off again in order to see the influence of light in our system. And here at table 4, we have the photocatalytic activity measurements of the palladium containing samples. The results are an average of the product formation during the light on injections. The results are at micromoles per hour per gram of photocatalyst. And first, you can see that pure zinc oxide seems to have selectivity for carbon dioxide production and a slight production of ethane and carbon monoxide here. And the palladium containing samples seems to enhance the zinc oxide photoactivity. We have the ethane as main product, as we can see in here. And comparing both size photocatalysts, we can see that the ethane is the main product, and the ratio between ethane and carbon dioxide formation, comparing the both synthesized samples, is different. In the alcohol reduction samples, we see a ratio of around 7. When the borohydride samples, this ratio is almost 1, suggesting a more selective way for the ethane production in the borohydride samples. Besides that, we have ethene as a secondary product in borohydride method, and propane and butane have very slight amount of these products are produced. And carbon monoxide, comparing the pure zinc oxide and the palladium containing samples, we see the formation is get lower with the palladium containing samples. At figure 20 and 21, we have the products formation profile during the injections. At 1 and 2, the light was off, so we have no products formation. When the light was turned on, and injections 3 to 9, and here, the activity is higher. We have the product formation. And then when the light is turned off again, the activity drops down. So as conclusions, we have that both synthesis methods were successful for the palladium nanoparticles production. We have that the borohydride method, it's more efficient than the alcohol reduction method at producing nanoparticles, dispersive nanoparticles and smaller. And this palladium seems to enhance the zinc oxide photoactivity, having ethane as main product and ethene as secondary product. And we can see that the size and dispersion of the particle might play an important role in the conversion of methane at this photocatalyst. I'd like to thank everyone, first my group colleagues, all the institutions, and everyone here. Thank you.
Very nice, Alf. Thank you very much. Questions? Ernesto, you got the first.
So thank you by this nice presentation. I'm just asked because you detect about 1% of palladium over the surface. And you got also the image. I think that the image in the slide 11. Did you count if the covering area of the palladium, no, another one, this one? Did you count how much of the surface area is covered by palladium?
No, we didn't. To be honest, I did some histograms measuring these particles using LINS program, but we need some techniques like, I think, sorry, I'm trying to remember the name of the technique. Chemisorption. I think chemisorption analysis might give us the surface that palladium is having around the surface particles of the semiconductor.
The reason for my question is, it seems to me that you have much more than 1% of palladium over this point. So you need to, if you want to, you need to got different areas, different positions, and just check.
Thank you. It's we might do this.
Good point. Okay. Any other question? Okay, guys. So thank you very much.
Thank you, everyone.
So we move to the next presentation here. Priscila Zambiase, please. São as setinhas laterais. Okay, Priscila.
Okay, Professor, thank you.
Thank you very much.
So I'm Priscila. I will present the design of catalyst-based palladium for conversion of methane to methanol in fuel cell system. And the first time I would like to thank for the Professor Fabio and the Professor Almir for the opportunity to stay here to talk about this project. So, Okay, so in the first time I would like to present the research group coordinated by the Professor Almir Oliveira Neto. And this project provides to this conversion of methane to methanol by use the electrochemical device by fuel cell system. So according to the IPCC record, the last report, the emission of the greenhouse gases is very critical in the last years, because here we have the high emissions of the methane, and compare with to a carbon dioxide, this molecule, the methane is more aggressive, because this component retain 25 times more heat of heat higher than the carbon dioxide. So because this is very important, we reduce this emission of this gas and to decrease the peak of global warming. So modeling the mitigation pathways to limit this warming to 1.5 degree and or 2 degree involve the and happen sustainable emission reduction. So in this view, the methane, we know this molecule is a simple alkane, and with this fact is acting a building block to bulk other organic compounds, and is useful fuel source with the high calorific capacity. So this is very important to convert to this methane to conversion to value-added products. And for this, we need more technology advantage. And for example, this methane to convert it to methanol is important to do these compounds with the clean and renewable fuels and useful energy to provide a green electric energy. And so besides from the methane conversion, we can provide other molecules, organic compounds, such as organic acids, alcohols, or aromatic compounds, and ester and or esters. So in view of the many technologies provide us to convert methane, the oxidation, the selective oxidation of methane to methanol, I talk about the fuel cell system because this electrochemical device is promised device to generate green energy, and besides other products from the methane conversion. So in view this fuel cell system, the polymeric membrane reactor fuel cell types, we look forward to many advantages of this device, and we look for the fabrication and assembly of this system and electrochemical analysis, and in addition, the catalyst and design synthesis and nanoparticle formation. So for us, we look in front of this advantage of this fuel cell system, we have some challenges to have more high efficiency and activity of this device, such as the durability of these materials, and in addition, these electrocatalysis, and the selectivity of formation, the organic products, and the electrocatalysis efficiency. So in view of this all problem and challenging, the project work with this, obtain the palladium electrocatalysis to promote the methane to methanol. And Nandeng in this work, Nandeng described this chemoabsorption of methane on metal catalyst surface. And here we observe this, there are some presence of some oxygen spaces covering the electrode surface. And here we obtain this electrocatalyzed by the reduction process with the borohydride. So later, Boyd described this effect of the methane absorbed on the metal surface catalysts, and they describe this formation of these oxygen spaces, and in addition, these radicals, alkane radicals. So besides these results, we can observe the formation of the other organic molecules, like to formic acid and besides methanol. by the in situ experiment with the infrared spectra with electrochemical cells. So furthermore, we have the polarization curves and the power density, and we observe that the palladium electrocatalyst results in the more open circuit potential and the high power density. So, in view of these results, Souza described this activity with replace the use hydrogen peroxide together with methane in the reactor and analyze the products formed by the quantification on Raman and by the qualification using the infrared spectrum. So with the electrocatalyzed of platinum supporting carbon, we observe the formation of hydroxyl radicals. So here, the authors observe there are a synergic affection of this formation, the oxygen reactive spaces to attack the methane to form other products such as methanol. And here we have the quantification of methanol production. So in compare with the last results, here we compare when we use the water vapor in the reactor. So here we analyze the water activation to form the oxygen spaces, reactive spaces. So in this case, when we use palladium platinum electrocatalysis, we observe that mechanism electrochemical reaction we have the water activation, and this is necessary to attack the methane to form the other products. So, and we have the control of the potential applying the reactor. We have we can mapping the formation of the other products, such as ether or formic acids besides methanol and formaldehyde. And so, viewed all electrocatalysts obtained during this research, we look for this platinum or palladium catalysts and other bimetallic catalysts together with palladium, such as copper doped with palladium supporting carbon palladium. So, to compare the durability and selective formation, the products and efficiency of these electrocatalysts, we replace this and use new active support, such as metal oxide. And we observe when we use titanium dioxide, we have more production of methanol and in more times operation. However, when we look for the efficiency conversion of methane to methanol, we can compare when we use water and peroxide hydrogen, and we look for we observe the more efficiency when we use the water for water activation. So in this mechanism reaction, we observe the Faraday and no Faraday process, the mix of this process. When we have the Faraday, we obtain the oxygen spaces, reactive spaces, and these immigrate from the reactor chamber to attack the methane to form the other products in a no Faraday process. So in this mechanism, we can observe this cogeneration of electric energy. And with the electropotential mapping to obtain, we can observe the formation of other products besides methanol. So in all results, we can have some scientific contribution with the methane to convert to methanol. And we have some advanced solution in the fuel cell system, in the fuel cells device. And in the first time, we use a reactor based on carbonaceous materials. And due to the fact we have some oxygen reactive spaces forming the mechanism reaction, these spaces attack these carbonaceous materials. And so to confer more durability of these materials, we replace steel plates to protect against these oxygen reactive spaces. And in addition, we produce this proton exchange membrane by for the use of the gas diffusion layer to control is just to control the hydrophobicity of these materials. So in addition, for this membrane exchange assembly, we look for to replace the naphthalene for more efficiency or reduce the cost. So here we produce this membrane, use the boron nitrate exfoliated with the graphene. So here, when we compare this activity of methanol production, compare this new membrane with naphthalene, we have a good efficiency to form methanol. But the durability is good, but is not efficiency for this. But we look for this more durability and selective for this this product. And besides the electrocatalyst synthesis, we work with the second generation electrocatalysts in view to confer the more durability and use new support, active support, like as bidimensional nanostructure, such as nitrate, metallic nitrate, and other materials to confer more durability and selective for the formation of methanol. So with all these results, we look forward to new ways, new pathways when we use methane to convert methane in other products. So we can use for hydrogen shift, for hydrogen economy, and to obtain new nitrogen spaces by the modified the analytes, and to obtain more complex organic compounds. So here when I talk about the hydrogen economy, by the when we use carbon dioxide or nitrogen as a reactant with the methane, we can obtain other products such as formaldehyde and besides methanol or formic acid. So here we observe in our activity the generation of this besides hydrogen, look materials such as ammonium and other nitrogen compounds, such as hydrazine, in this case. And in addition, this product we can use as a fuel, so such as formic acid, ammonium, or sugar energy is industrial waste, like as vinasse, to produce hydrogen. And because you look forward to green energy and other chemical products. So thank you for your attention. I have a few time to show many results. Thank you.
If you have questions, you have time for one question. Professor Ernesto.
Thank you, Priscilla, for this very nice talk. I'm just wondering why the open circuit potential changes when you add palladium to the system. Slide 10, you show that. I think that is 10. Yes, yes.
Here we have the high open circuit potential for the palladium. Here we believe there are some synergy between this formation, the oxygen reduction reaction, and the methane activation. Yes. But when we have the open circuit potential, we have the some. So can I say we can observe the electron transfer? So.
Okay. Thank you. Any comments, questions? Okay.
Okay.
Thank you very much.
Thank you, Professor. Thank you.
And we move now to our next presentation, given by Andrei Barbosa, PhD student under the supervision of Professor Elizabeth Santiago. Andrei.
Hi, everyone. My name is Andrei. I'm a PhD student of Project 14 in M2P program. Professor Dr. Elizabeth Santiago is my supervisor. And recently, we have dedicated to convert methane into products. The title of my presentation is HDP based on ion exchange membranes for methane conversion devices. And okay. And on general context, the methane is a product of natural gas that is a product of oil exploration. And in addition, methane is a pollutant gas responsible for greenhouse effect. In summary, methane, it's extremely important that methane to convert it to other products that are less aggressive to environmental. There are several ways to activate methane, such as partial oxidation reaction by electrochemical devices based on ion exchange membrane. There's a large interest, the application. Devices based on ion exchange membrane became well known for the application in fuel cell, and because they have a high performance and good stability, and it's possible to use a platinum-free catalyst. In this work, the membrane is prepared by radiation-induced graphite method, whereas a starting polymeric film is irradiated and grafted with an monomer after emanated to form an ion conduction structure for carbonate activate methane. Before conversion test, the membrane was optimized for have an ion exchange membrane with a high conductivity, and consequently we can observe an ion exchange membrane with high performance for fuel cell tests. Here is the proposal reactor pathway for activating methane with carbonate. You can see several compounds, which is alcohol, ketones, carbonyl compounds. So this is the electrochemical reactor configuration. We can observe platinum carbon at cathode for oxygen redox reactor, and one bifunctional catalyst based on cerium zirconium at anode for methane oxidation. The cathode is supplied with one mixture of 30% CO2 and oxygen with some conditions such as temperature, flow, and catalyst load, and vary to the potential. The product was collected at anode outlet and injected into GC feeds by headspace method. The product was obtained using the concentration of products was obtained using one calibration curves for each product. And session result after identification and quantification, we obtained several compounds, alcohol, aldehydes, ketones. The methanol is the product in greater quantity than the other compounds. 1 volt is the best potential to methanol formation. And finally, it's possible observe one comparison and an ion exchange membrane carbonate form and hydroxyl form, and when possible observe that the concentration of products is lower when they use hydroxyl IAM form. Thanks.
Thank you, Andre. We have time for questions. We can either choose a lot of questions or get back into the scheduled time. So, Andre, any comments?
Professor Elizabeth.
Okay, I'll measure.
What's the difference in carbonating form
forming any hydroxyl form in production of methanol.
Hydroxyl is nucleophile. É um nucleófilo mais forte, né? Então.
Maybe because
Yes. Então, na verdade, eu vou responder em português, tá, gente, por favor. Quando a gente faz a membrana em meio OH, né, por isso que eu lá no início faço um teste de célula combustível para ver se a nossa membrana está funcionando, né, mas a reação em meio alcalino para OH ela é diferente, né, a gente sabe, ela está tentando fazer com CO2 para fazer o carbonato lá na reação de redução, né, de oxigênio, mas a configuração da reação é diferente quando a gente está em meio OH. O OH é um nucleófilo mais forte, né? Então ele vai oxidar o metanol de uma forma mais severa e você vai, consequentemente, ter mais CO2, né? Por isso que o metanol está em menor quantidade ali entre os produtos. Né? A gente tem o metanol aqui com menor quantidade. Essa linha aqui, gente, é a linha de quantificação, tá? Então, por exemplo, quando a gente está no meio OH, a quantidade de metanol, por exemplo, já está abaixo, ela é identificada, mas está bem abaixo do que a gente consegue quantificar. Né? Isso é uma questão também do equipamento que a gente usa, né? da metodologia. Então, a gente não tem analisado os leves ainda, só a parte líquida dos produtos. Então, levantando a metodologia para quantificar a parte dos gases, né? Mas a gente tem uma ideia de que pelo menos está constante, mas ainda não conseguimos quantificar. É isso.
Okay, thank you. Okay, let's thank again our speaker. And we move now to the last presentation before the break. Nicole. Okay. So our next presenter is Nicole Bogosian Patricio. Thank you very much, Nicole.
Good morning, everyone. My name is Nicole Bogosian Patricio, as Fabio just said. My work is series zirconia bifunctional electrocatalyst for electrochemical conversion of methane. And the main authors are me, Juliano Carvalho, and Elizabeth Inácio Santiago, my advisor. Talking a little bit about methane. Methane is the simplest alkane and the building molecule of most organic compounds on Earth. It is the main component of natural gas too, 70 to 90%, and a potent greenhouse gas, being 25 times more pollutant than CO2 itself. Methane is a very stable molecule because of its CH bonds that are really hard to break. Because of that, it's very difficult to partially oxidate it. And once you give the energy necessary to break this bond, you end up activating the intermediate products that are the products that we really are interested in. So because of that, it's really difficult to find catalysts that can contain this excessive oxidation to CO2 of the products that we are interested in, and to find catalysts that have high selectivity for products of higher added values. Here I point out two works that use carbonate ions as source of O2 that makes able to oxidate methane to most, in this case, methanol. And the pioneer was Spinner and Mustaine. They used zirconia and nickel oxide by function of electrocatalyst, nickel oxide to activate methane, and zirconia, not only in this work, but in both of them, to facilitate the absorption of carbonate ions. It can do it because it has Lewis acid sites and the ability to accept electrons, facilitating it. Nickel oxide in this work, although exhibited low catalytic activity to the electrooxidation of methane to methanol. And then in a posterior work, Matt et al., inspired by Spinner and Mustaine, used cobalt oxide and zirconia. In this case, the cobalt oxide to activate methane, and it showed catalytic superiority in comparison to nickel oxide. Although the cobalt oxide wasn't able to oxidize methane by itself, showing the need of zirconia. As we see, they use here zirconia and then other metal oxide, zirconia to absorb carbonate, and we need another one to absorb methane. In our work, we chose Syria because it has the catalytic activity for methane. It has acid sites that are able to break the CH bond, and as the other metal oxides are able to produce alcohol. Platinum, for example, tends to produce 100% of CO2. Also, Syria has low cost in comparison to other noble metals and has a really strong synergy with zirconia, forming Syria zirconia. Here I start showing the synthesis, and we use the microwave hydrothermal system. In the first path we took, we mixed the serous nitrate hexahydrate with the zirconyl nitrate hydrate, and to form the solid solutions that we referred as CZ. In the second path, we first synthesized zirconia and Syria, then zirconia was mixed with serous nitrate hexahydrate, while Syria was mixed with zirconyl nitrate hydrate. They then passed for another time in the microwave, forming the CPZ and PCZ that were Syria grown over zirconia and zirconia grown over Syria. We used the mass ratios of 1:1, 1:2, and 2:1, and the synthesis was carried on over 200 degrees for 30 minutes. Here there's a scheme of the half cell I used and a photo of it, and we can see that the work electrodes were CPZ, PCZ, and CZ. As reference, we used silver chloride, and as counter electrode, we used platinum. Nitrogen was bubbled for 30 minutes, and then we ran cyclic voltammetry, and then methane was bubbled for an hour, again running cyclic voltammetry. These results were subtracted one for another, and then we had a resultant voltammogram of which we took the peaks, current peaks, and found the potentials that we use to apply to form products. Starting to show the results, first we have the Xrds. These are the Photograms of CPZ, PCZ, and CZ. And we can see that as expected, Syria was crystallized in cubic phase, while zirconia was crystallized in monoclinic and tetragonal phase. I believe that we were able to get tetragonal phase because we used the microwave system, because it allows us to reach metastable phases in smaller temperatures. We can see that for CPZ and PCZ, there are both peaks of Syria and zirconia, showing that we have both oxides in its composition, while for CZ, we don't have the specific peaks of Syria and zirconia. We have intermediate peaks between Syria and zirconia, showing that we achieved here a solid solution as expected. Here we have the transmission electron microscopy images, and we can see a certain uniformity of the particles. We have mostly a circular and rectangular morphology for CPZ and PCZ, and these are all for ratio 2:1. And for CZ, they are actually a little disformed and difficult to see the contour of the particles, but we were able to measure the particle size average, and for CPZ we have 7.6 nanometers, PCZ 8.9 nanometers, and for CZ 5.4 nanometers, all of them really smaller than what was found in literature, again, because of the use of the microwave hydrothermal. In literature, they all use conventional hydrothermal precipitation and co-precipitation. Here we have the scanning of all products formed, and they were identified and quantified by gas chromatography. We can see that the highest product formation were obtained for ratio 1:1, but the efficiencies were really low. The ratio 2:1, by the other hand, showed the greatest efficiencies for all configurations, CPZ, PCZ, and CZ. But for CPZ, we were able to achieve 15.3% Faraday efficiency for methanol, 17.4% efficiency for ethanol, and 15.7% for acetone. Because of that, we chose the 2:1 ratio to proceed this study. So here we compare the 1 milligram with the 5 milligram loads. And we can see that for a higher load, the product formation ended up being really smaller, not even reaching the quantifiable limits that are shown by these dashed lines. I didn't talk about it in the other slide, but that's it. And we assume that, and the Faraday efficiency as well was really lower for the 5 milligram per centimeter squared load. And we can assume that there is a relation between the load and the thickness of the electrocatalytic layer that leads to a higher compaction of the electrocatalyst. And this compaction ends up limiting methane absorption sites on the electrode surface. And that probably it makes more favorable the oxygen evolution reaction. The small traces of CO2 that were found both for 1 and 5 milligram per centimeter squared loads also indicate that is the oxygen evolution reaction that is being favored. Here we have selectivity, and for methanol, the configurations that had the most selectivity, that are more selective, are CPZ with 53% and PCZ with 62%. And for ethanol, it is CZ with 44%. And that's it. Thank you very much for your attention and for everyone online. And thank you, CINE, FAPESP, and Shell for all the support.
Thank you very much, Nicole. Very nice presentation. Questions from the audience, comments? Ernesto.
Yeah, it's a very nice talk, and I'm thinking why they are different. The CPZ and the different, and what do you think about that? Because from a structural point of view, or do you think that we're just talking about the surface states that are different, or What do you think about that?
I think the difference is mostly because there are the two oxides, and then the goal was actually to make one oxide being side by side with another, Syria and zirconia. We don't actually know if this was possible, but one has to absorb carbonate and the other has to absorb methane. So I believe that when we have just Syria and zirconia mixed in solid solution form, they just can't do the same way that one oxide can do when it's next to the other.
Did you have the opportunity to make some kind of IPR measurements, paramagnetic resonance measurements?
No.
Because I'm wondering if we have a change in the oxidation state of cerium, which there is to occur.
No.
XPS measurements. We are treating the results, and probably we have a relation with the relationship with the state, yeah. Operative state. That yes can answer it.
Okay, any comments?
Okay, Mr. Fernando, you can talk.
If you have a question, if you're online, you can type your question in the chat. You can use the chat function so we can answer your question. Meanwhile, yeah, André.
Fiquei curioso que o seu material com menos catalisador teve uma resposta muito superior, né? Vocês chegaram a ver a morfologia?
Não, na verdade eu vou pintar hoje para saber se para daí passar por fazer uma imagem de transmissão ou de varredura para conseguir ver essa espessura e ver se isso tem alguma relação mesmo.
Tá. Outra pergunta também parecida. Quão importante você acha que é a área superficial nesse caso? Porque a comparação da literatura aí tem catalisador de micron, outros de centena de... Você acha que é crítico isso?
Não,
ou...
Teoricamente é crítica, né? A área superficial. Só que, por exemplo, na literatura, uma conseguiu uma eficiência de 40%, a Maerol, inclusive, com óxido de cobalto. Só que ela deixou muito mais tempo, né? O metano saturando no eletrólito. Então, acho que tem várias questões que tem que ser levadas em consideração, mas com certeza a área superficial é um ponto crítico, sim.
Okay, thank you. Any other questions? We got the online one? No? Okay.
Obrigada.
Okay, so if you have any questions left, I would like to thank all the speakers to keep up with the timing, and all the audience here and online as well. We have a break now. We come back at Danielle, the schedule. We come back at 11:30. So we're gonna have our invited guest Cauê Ribeiro. Professor Cauê Ribeiro will close this morning's session, and we restart at 11:30. We have a break. Stretch your legs. The ones that have the lucky to be here with us, we're gonna have some some snacks outside. Okay, time to catch up. Thank you very much.
Alô, Cauê, você me ouve?
Daniel, me ouve bem?
Sim, te ouço bem. Espera aí.
Daniel, me ouve bem? Eu não te ouço.
Alô, Cauê, tudo bem?
Tudo bem, tudo bem. Agora eu estou te ouvindo.
Eu tenho que ativar o... Peraí que tá dando um eco terrível aqui.
Daniel, você quer fazer um teste do compartilhamento de tela?
Coloca aí um minutinho. Vou fazer isso. Vou mudar de computador. Um minuto.
Não, tá ótimo.
Cauê.
De volta. Estão me ouvindo bem?
Oi, Cauê, tá ótimo, estamos te ouvindo bem.
Tá perfeito. Tá perfeito.
Você quer compartilhar sua tela para ver se
Isso,
fica em ordem?
isso, eu queria testar a tela. Tá, eu tô com um problema na câmera, porque eu tive que mudar de computador. A internet caiu dentro da Embrapa, eu tive que voltar correndo para casa. Tive que voltar para casa para resolver. Mas se você estiver me ouvindo bem e aí o compartilhamento estiver ok, aí eu acho que não tem problema.
Eu estou te ouvindo bem, ainda não compartilhou aqui.
Espera aí, eu tô colocando no modo de apresentação aqui primeiro, só para ver se... Eu estou com duas telas aqui, eu coloquei no meu celular aqui do lado, eu coloquei no meu celular aqui ao lado para poder... Deixa eu ver aqui, se ele está indo ok. Parece que está perfeito, né? Está perfeito, né? Deixa eu tentar só uma outra coisinha aqui no compartilhamento, eu vou tentar de outra forma aqui, só para ver se ele vai bem. Eu consegui acompanhar a passagem de slides.
Você quer que eu fale alguma coisa sobre a sua digníssima pessoa antes da introdução?
Aqui caiu a reunião aqui. Está correto isso? Caiu o Zoom para todo mundo?
Não, nós estamos aqui.
Tá no
Não, está aqui.
Então, peraí.
Sem compartilhamento.
Peraí, deixa eu ver o que aconteceu então com o meu aqui. Não, é que como eu falei, eu tô o seguinte, eu estou com uma tela, eu estou com um celular aqui do lado, eu consegui ver o que vocês estão vendo. Entendeu?
Você está com duas contas.
Esse que é o problema. Só que aí ele caiu um aqui, porque senão voltou. Peraí, ainda não está do jeito que eu quero.
Aí, agora eu estou com a sua apresentação ok aqui.
O problema é que ela não está do jeito que era para ser. Estou tentando. Porque eu quero que ele coloque aqui o contador de tempo. Porque senão eu não vou conseguir acompanhar, né, vocês. Para não falar até as 14h. Está novamente correto?
Aqui está ok.
Perfeito. Então, ótimo. Agora deixa eu só reconectar aqui para eu poder garantir que eu consiga ver o que vocês estão vendo. O online ele tem esses problemas, né? A gente tem que ficar fazendo um monte de gambiarra, né? Para poder funcionar do jeito que a gente quer. Eu acho que é só apresentar o geral mesmo. Fica à vontade para falar sobre minha pessoa. Fale dos contatos do passado.
Você não pretende abrir uma câmera para a gente te ver, não? Você vai deixar?
Não consigo. Eu não consigo. Porque eu tive que trocar o computador. Eu tive que pegar um outro computador aqui. Entendeu?
Faz uma troca de slide.
A internet caiu no Embrapa e aí eu tive que voltar para casa.
Entendi. Não.
Entendeu? Eu estava hoje, agora de manhã deu problema lá e até quando caiu aqui eu falei, será que só falta ser problema com o tronco da FAPESP? Eu falei, bom, agora eu tive que pegar um computador sem acesso consistente. Ele tem um webcam, mas eu tentei o webcam dele, ela está totalmente desconfigurada, ela está esquisita. Não dá para ver nada.
Beleza. Então, eu acho que está funcionando. A gente começa daqui 2, 3 minutinhos.
Está perfeito.
Espera aí, até daqui a pouco.
Deixar aqui no meu mudo. Deixar no mudo aqui.
O pessoal vai entrar na sala aqui de volta, a gente já reinicia, Cauê.
Tá ótimo.
Hello, everyone. We are back to our final seminar this morning. It's a pleasure for us to have here Dr. Cauê Ribeiro. Cauê has joined the Methane to Products program recently as one of our investigators, and he has been contributing with different works here. And it's a pleasure that we have your company this morning. It's a shame that you cannot attend personally, Cauê, but we are happy that you could accept our invitation and give us this talk today.
Thank you, Fabio. Thank you, everyone. I'm so glad of this opportunity to talk to you during this morning. Unfortunately, I have had some problems, some particular problems to travel to São Paulo today, and meanwhile we have had some problems in our internet connection there in Embrapa, my institute. So I have been forced to change everything in the very last minute to give this talk to you. But I hope that you can we can understand what we are trying to talk to you today. I really hope that we can start in this conversation an avenue for new cooperations, new ideas together. And again, I thank all of you, especially you, Fabio and Elizabeth, that have been the drivers for my coming to the CINE project, where I think that we can do a lot of things together, and think on new ideas for the future. As I have proposed to talk to you, initially, I would like to thank my group, my students, my postdocs that are doing the hard work actually in the laboratories. They are people we need to acknowledge all the time, because they are doing they are in fact doing the research. And also our supporters, our financial supporting that we have from some private companies like the CBOs and the ICL company, ICL and Dynamical company, that are giving support for us now, and especially for FAPESP with this nice initiative of the CINE Center, and also in the FAPESP agreement, which we are starting to work on that right now. Especially, I have a special acknowledgement through the CINE Nano program that is sponsoring our laboratory, the National Laboratory of Nanotechnology for Agriculture. Our institution is we are an institute of the federal government, but we are linked to the Ministry of Agriculture, not to the Ministry of Science and Technology like the IPEN is. In the Ministry of Agriculture, naturally, we have all our research devoted to find solutions for agriculture and related areas such as cattle production, the agro-industry, and etc. So now, currently, we are 43 different research centers distributed along the country. We are around 8,000 employees with 2,000 researchers, permanent researchers, but we have now a huge cooperation with different universities and other institutes that is allowing us to receive postdocs, students, masters, PhDs, etc., which are doing research with us. Currently, we are very proud to say that the investment in Embrapa is returning a significant amount in terms of income for this society, which is estimated in 70 per one, or in other words, 70 reais, $70 per $1 applied in Embrapa is have been returned to the society as benefits, goods, and other investments to the society. It's counting all the investments that we have in Embrapa, but also counting all the effects that Embrapa has impacting the society. For instance, different kind of seeds, different practices, agricultural practices, etc., but also the technologies we are doing catalysis right now. And these technologies are under the umbrella of this network of research called the AgroNano Network. This is a research network that has been founded in 2007. We are going to the 15 years of this network. And among these topics we have in this network, some of them include the catalysis, the development of catalysts, and its utilization in environmental decontamination and in production of agri-fuels. That idea of agri-fuels for us is wider than you can imagine, because in the first moment, normally we used to think in agri-fuels as ethanol. Ethanol is most in biodiesel, but ethanol is the most well-succeeded example that we have of agri-fuels in the world till now. But we are under this situation of CO2 emission and methane emission that is a problem, agricultural problem as well. So among the most important emissions of methane that we have in the world today, almost half of them come from agricultural practices. For instance, the production of methane is, you know, that the production of methane is represented by the emission from cattle production, from the breath of cattle, but also from the composting activity of organic residues in general. This comes from the last report of the IPCC this year, and the last report of the IPCC. One of the most interesting advices there is the awareness about the risk of the avoidable emissions. What do we say about avoidable emissions? Are those emissions that could be controlled by other means, avoiding its directly emission to the environment. For instance, the methane is the most typical example. We have in methane not too huge difference, but you can see a difference of the fossil origin of methane in terms of impact, and the non-fossil origin of methane in terms of impact. What this means? The methane from fossil origin is for us the methane explored by as natural gas. The methane of non-fossil origin is the methane that has been produced by, the methane that has been produced by composting. And so these numbers are the most updated, up-to-date numbers in terms of environmental impact. Means that we have an impact of almost 30 times the emission of methane compared with the emission of the same amount of CO2, which means that this amount that has been estimated for 2012, this is not up to date. We have more methane produced and emitted today, represents more in terms of effect for global warming than all the 35 billions of carbon dioxide emitted by every year. Means that if you have, we can treat and avoid this emission in the atmosphere, we could have a good reduction in terms of the total effect. But again, we are under the requirements of agricultural science here in our institution, and we are looking for solutions for these emissions of CO2 that we have, for instance, in ethanol fermentation. This is a very specific case, a very specific and illustrative case that we have in agro-industry. Because there, in that case, we have, by the briefing of the microorganisms, we have an emission of almost 1 kilogram of CO2, high purity CO2 per kilogram of ethanol produced. This today is one of the most important impacts that we have in methanol production in terms of global warming. Again, if we have some alternative to reuse or sequester or contain the CO2 and avoid this emission through the atmosphere, this would reduce in a significant amount the carbon footprint of ethanol. On the other hand, we have the methane produced by the composting that I have mentioned before. And this is an example that you have probably seen in the newspaper. The Gramacho landfill there in Rio de Janeiro is one of the largest landfills that we have today in Brazil. And there is an estimation of 70 trillions of cubic meters of biogas per year produced there in this region, in this area. We have other initiatives, for instance, the biodigesting program that we have in Brapa, which is focused on the production of methane in small properties, in small production. Using this methane for heating, for instance. This is only for heating till the moment. But recently, we have seen some other initiatives, for instance, this one that have been recently published in the general public article, explaining the possibility of using the residues of ethanol production to produce methane by composting as well. The idea of this production of methane into the same site is to integrate the production of one fuel with another one. And look to that, because this is actually agri-fuel. This is actually a totally renewable biofuel, because we are using the potential, of all the biomass produced in ethanol to produce another biofuel, apart from ethanol, that can be used to produce, for instance, heat. In that case, specifically in that case, we found some initiatives, some commercial initiatives. For instance, this one that has been published in unfortunately in Portuguese, but has been published in the last month. An article discussing the interest of Raízen. Raízen is the joint venture of the Shell company with Cosan in Brazil to produce ethanol in the production of biomethane in São Paulo. But also they have disclosed the interest to do this in all the other production ethanol productions in Brazil, which means that we will have in 10 years, a localized production of methane and with a production of CO2 in the same place. That means that we have a good window of opportunity to use both gases in an integrated production, an integrated system to produce something. And the something that we are interested to do is to think in an ideal system like this one that would integrate the production of methanol using CO2 and methanol using methane on the other side in the same electrochemical cell. Actually, we are pretty far off this situation. We are really far from the situation. We cannot say that we are going faster to this, but maybe these 10 years until we will have the infrastructure to that are enough to us to develop the most critical part of the system. The catalyst to do this in an integrated manner. Till now, we are more understanding how to do this in terms of a system like this one. You know the system better than me. You there guys in ABPEN, you know the system better than me. But understanding how to produce the catalysts in the membrane system to produce both reactions at the same time. So, why methane is interesting in this system? The most important term, the most important information that we need to manage to do this is initially to understand that the CO2 reduction is in general more more advantageous than the hydrogen production, except on the fact that we need more electrons to produce the same amount of methanol that we have for hydrogen. So comparing the potential that we need, these potentials are all in pH 7 to produce methanol from CO2, and the potentials that we need for to produce the hydrogen, we have a quite we have some advantage in this proposition. But the best, the better situation that we have is comparing the potential to produce methane, methanol from methane, oxidized methanol to methane, compared to the production of oxygen from water, which would be the counter reaction if we decide to do this in the current way the typical groups are doing CO2 reduction in the world nowadays. So the problem is still how to promote this reaction using some source of energy. Doesn't make sense to use, for instance, conventional energy to produce these reactions. But we are in a good moment for that. The moment that we have now is the down of the prices, international prices of photovoltaic panels, means that the energy, the solar energy, is going down so fast. This is the chart that we have for the different prices of solar PV modules worldwide today. We are going down so fast, and probably we are going to a competitive price of this energy in the next 10 to 20 years. Actually, this is a problem that we are still. This is a problem that is still unclear for most of the people, because actually the price of the solar energy is still more expensive than the other prices, especially here in Brazil, for comparing to the hydroelectricity power. But when we compare these prices with the prices, for instance, of the thermic produced electrical energy, we are below this price now. The problem is still how to use this in a consistent system that can use this in an organized manner, like we have for this that example for electrolyzer, a simple conventional electrolyzer that like this one. I am trying to start the video. But the general idea is to use the electrical energy coming from the solar panel to drive the energy, to drive the reaction, producing, for instance, in that case, this is an example for hydrogen, but the example for CO2 is exactly the same. But after that, you can use this in a fuel cell, you can use this as a source of energy for chemicals, etc., and so on. That's not a problem. That's not a problem to use the stored energy. The problem is how to produce this stored energy. We have another advantage to think on CO2 reduction instead of hydrogen production, is that comparing the limit, wide Shockley price limit of hydrogen production from solar light and the production of hydrocarbons, in principle, we are in a better situation for doing hydrocarbons. For instance, we can increase the amount, the limit, the theoretical limit for the hydrogen production using solar light, using this kind of device, is 90%. But we can go better if you think, for instance, in ethane, ethanol, methanol, and all of them going over 26% in most of these cases in terms of utilization of solar light. That's important to remember that the limit of the Shockley-Queisser limit, the limit of solar light utilization to produce energy is 35%, which is defined by the Shockley-Queisser limit. This is why we have the difference of the double junction and the triple junction in the different systems. But again, the most important part of our problem is how to understand the limits of these reactions, and we have a list of different challenges. For us, we are still in the first step. We are in the catalyst discovery, finding ways to produce catalysts that can be cost equilibrated, with good repeatability, because they need to be used during long times, and durable. And these are the problems we are still facing in this talk. The other talks are still open. For instance, the design of the catalyst, if we are talking about powder versus supported catalysts, the utilization of photovoltaics plus electrolyzers, or the direct utilization of light over the catalysts. Both of them are still a question for us. And the device project and assembly, which is still a question for almost all of us. So, for specifically in the case, specifically for the case of CO2 reduction, we are still discussing the best catalyst for that and for the electrochemical systems. We know that the monoxide production can be achieved using some different noble metals, especially silver is one of the most interesting till the moment, with an adequate over potential, but to do some other systems using binding the carbon with hydrogen, we need to use other materials, especially copper oxide and copper oxides. So the problem is still the over potential that we have for these systems. But till the moment, the most promising material is certainly the copper oxide, because this is almost stable. We have good, we have a good equilibrium in terms of price. The recovery of the catalyst is still easy, but we are still with problems in terms of how to increase the current density of this catalyst and how to produce this in a simple system, like we have done, for instance, for hydrogen along the time. So we have proposed to do a similar system, like we are we used to do for hydrogen, making an ink of copper over carbon for carbon black, and using this system as a templated assisted synthesis to promote a better catalytic distribution. We can see that we can, using this kind of electrodes, we have the production of too much hydrogen. This is clear to see by the bubbles forming over the surface on the system. But the most interesting part of this system is to understand how we have the Faraday coefficients of CO2 reduction over the system. Till now, our problem is how to control the Faraday, to control the preference of the system to reduce CO2 instead of reducing water. So although we have a good performance, a good current density of these electrodes, we are still producing too much hydrogen. You can see that we have a high production of hydrogen in these systems. But since we have different conditions to produce this using different potentials, we can tune the system to produce more liquid hydrocarbons. For us, it's more interesting to have more the production of these liquid hydrocarbons because we are closer to the target condition that we are looking forward, which is the methanol on both sides. But we are still trying different catalysts. For instance, the bismuth oxycarbonate. And the bismuth oxycarbonate has some advantages in terms of liquid production of liquid fractions, but still not the methanol, but more the formcast. The formate can be produced by this catalyst with Faraday efficiency of 70%, which is good compared with the other efficiencies that we have in the literature. But the most interesting aspect that we got using this strategy is to increase the current density of these catalysts. We see in the literature that we have some examples like this one used as a reference for us, the sulfur doped indium, which can have current densities around 100 milliampere per square centimeter, which is a target for us. But till using the bismuth oxycarbonate, we got a current density of 50 milliampere per square centimeter, which is a good number for this the current stage of our research. But again, in terms of catalytic discovery, we need to use some kind of reference to understand how this catalyst could be interesting or not to produce CO2 reduction. And in our opinion, semiconductors are more interesting on this way if they are directly excited by an external source of light. The most important for us in selection of semiconductors is to understand where the conduction band of the semiconductors are in terms of these reactions, these reduction reactions. Thinking the system like an electrochemical cell, but an electrochemical cell in a particle. Or in other words, if the semiconductor receives the light, the electron is available to produce a reduction reaction, and the hole is available to produce an oxidation reaction in the same particle. In terms of the relative position of these reactions, most of the string semiconductors have adequate positions, but the problem is how to increase this interaction with the CO2. And what we can do is try to select the semiconductors using freestanding particles instead of electrodes. These freestanding particles, they have more interaction with CO2, and in most of these cases, we can analyze the products by analyzing, for instance, the liquid along the time, or analyzing the headspace after some while of some time of the reaction. Coming back to the copper oxides, the copper oxides are interesting even in that condition because we can think on them, as I said, a kind of electrochemical cell in the same particle. That these particles are submitted by a reduction potential when illuminated. This is the band gap of these are the requirements of the reaction. In one side, the particle will be submitted by submitted to a reduction reaction, the CO2 in that case, and the other side submitted to production of oxygen, thinking that we are doing the reactions in water, but means that the site where the oxygen is evolving is naturally in an oxidized state, whereas the site where the reduction reaction is taking place is is reduced as copper. So, to confirm this hypothesis, we have produced different copper oxide morphologies with very high surface area. All of them are copper oxides, and we have submitted these materials to different conditions of reduction. For instance, in that case, we have studied, this is the starting material, just copper oxide. We have done the reaction of CO2 reduction reaction using water. We have observed after the reaction, a transformation of this material has changed to another phase. We have tried this in a basic, in an alkaline environment using sodium hydroxide and CO2 again. We have tried to use it, electron suppressor, the bromide, potassium bromide, to understand what we would produce in the system, and a system that is a whole suppressor with sodium oxalate. Just to understand the system, in that system we will have the reaction of the CO2 direct over the surface of the particles. In the second one, we'll have the formation of carbonate in the system. In the third one, we'll have the total suppression of the CO2 reduction, because we have some another system that will suppress all the electrons in the system. And in the last one, we have the total suppression of the holes in the system, means that we'll have the maximum possible CO2 reduction. And what we have seen in each system is the formation of the carbonate, the copper carbonate instead of oxide, except in the last system where we have seen the production of a metallic copper. This system in some way is confirming the idea that the light application with the CO2 is reducing the material, and all the reaction of CO2 reduction is taking place over the copper instead of over metallic copper instead of oxide, copper oxide. So in the other cases, we can come back to the idea of the Probert diagram. We can understand that the material has been eroded and is forming a second phase, a copper carbonate, by the contact with the CO2. Taking different cycles over this best system, we got a significant production of methane, but on the other hand, this significant production is going down so fast. This production, production is going down by poisoning, making copper carbonate over the surface, as we have proposed. Again, that the light is going to reduce the material, the copper, the original copper oxide, to copper, metallic copper, at least at the surface, and making the oxidation of the surface to copper carbonate. So how can we increase the stability of the system? The idea is to join the system with another semiconductor that can promote the separation of the electrons, by pumping out the electrons to one semiconductor and keeping now the holes to another semiconductor. Our choice for that system, that could be a Z-scan or a lateral structure, doesn't matter in that specific, in that moment, it doesn't matter. But the most interesting is to understand this in a practical example. For instance, the copper oxide supported over niobium oxide. Why niobium oxide? This is the idea was to find an oxide that could be much more stable than the copper oxide. And in other words, a system that at the end of the reaction could be enough to oxidize the copper oxide again, if the reaction comes with this, goes with this this model we have proposed. So these are the particles. The synthesis using this particle supported over niobium oxide, as you see here, and this is the diagram, the band diagram that we expected. The copper oxide is more prone to pump electrons or to concentrate the electrons in the conduction band, whereas the niobium oxide is more likely to have the concentration of the holes here in the anion oxide that would be responsible for the oxidation reactions. So what we observed is that this system is in fact more stable. It can be used in longer times than the system with only with copper oxide. And the most interesting part of this research was the tendency or the trend of the system to produce liquid products instead of gaseous products. The production of liquid products in this system is more interesting to us because we are going closer to the idea of methanol. Although we don't have methanol yet, we are dealing of formate and acetate, but we can see that we have more interaction to produce the methanol in that system. But so, going to the other side of the reaction, we talked about the idea of a system that could oxidize in a controlled manner the methane to methanol and to reduce the CO2 to methanol in the same system. So the ideal system would be a system that has both reactions taking place at the same time. And then we need to pay attention to the other side of the reaction. This is not this is a paper from the literature that has proposed the idea of using titanium oxide, as you know from other papers, to oxidize the methane in a controlled manner. But the most interesting part of this paper was to observe that very small amounts of transition metal oxides are essential to produce methanol. You can see that the production, the methane conversion rate that these authors got from titanium, pristine titanium oxide is not too different from the other systems. But on the other hand, the production of methanol is too low. This means that the system is going to the oxidation, the total oxidation of the methane to CO2 instead of oxidizing this in a controlled manner to methanol. So we have proposed to use a system that we are studying in our laboratories, in our cooperations with other Professor Ivo Teixeira in UFSCar. The utilization of carbon nitride as a support of different catalysts to oxidize this methane in a more controlled manner. The idea is that if we have single sites of specific metals, we can control better this reaction. And in fact, we got this using different metals. Over this structure, PHI is the structure of high exfoliated structure of carbon nitride, which have where we have used sodium as the template to be replaced by cobalt, iron, copper, etc. And we found very good production of methanol using on light over these systems modified with copper, and interesting again in very low amounts. Or in other words, the hypothesis that lower amounts of copper or lower amounts of modificants, they could be more interesting or more effective than higher amounts seems to be real. But it's more interesting to see in this research that we got this in copper, while in iron, which was the other the system that got better conditions in the other research, we have had a complete oxidation of the system, going more to CO2 instead of methanol. It's important to compare both the numbers. The comparison of both numbers is interesting because the oxidation, total oxidation of methane to CO2 is consuming more electrons than the partial oxidation. So the amount of the oxidation is comparable. The total amount of the oxidation is comparable in terms of electron transference. But the conversion is much better for the copper, because in that case, we are doing this in each molecule of methane, 1 per 1. So the next steps are to understand how the system works, and to understand how the system works, we need to check the amounts of copper over the surface. As we saw, the amount of methanol using copper over the methane copper over the carbon nitride is much better than we have seen in previous research, but we are still understanding how these amounts are related to the relative amount of each system. So this is a work in progress. We need to understand that we need to understand how to join both reactions still in the same system. And honestly, we are really far from practical applications. We need to be clear that what we are doing now is more science, understanding the system, than doing final application. For an example, to you understand some criteria we have in literature, one of these criteria is the solar to fuel process efficiency should be higher than 10%. The natural photosynthesis is something around 1%, means that we can produce an average of 7 trees using 1 ton of carbon dioxide. This is not too much. I understand that if you can join all this process in a integrated process that can get more than 1%, we probably are better. We probably will be better than the natural condition, but it's still far from a practical application. So we need to have this in mind. The catalyst durability is still a big problem in this experiment. For instance, the target that we use for hydrogen is 10,000 hours. The water splitting catalysts in some cases have been reported in 20,000 hours. We are not in that situation yet. In terms of catalyst selectivity, this is the third problem that we have on that. I mean, we are targeting the production of methanol. But till now, we are producing monoxide, methane, and other products, and hydrogen together in now the CO2 reduction. And that is the same of methane oxidation. We are producing other byproducts and going to, in some cases, to CO2 to complete oxidation to CO2, and we need to increase the catalyst selectivity. The coupled oxidation is something that we have discussed along this presentation. And the last one, and the most important critical question that we need to address, is the day and night of these reactions. We are limited in 5 to 6 hours per day because we don't have light during the night, which is obvious. So we need to have some kind of integration of these reactions, and we are still open for ideas in that question. The final one is the cost of the system. Actually, the cost of the system, from my opinion, it is the last one, because we need to have a feasible system before we start to discuss cost. But this is still, naturally, this is still an issue for all of us. We have done a summary of all these technologies and the challenges of these technologies in this paper that have been exactly in the last week published online. It is a review paper where we have a summary, a compendium of all these technologies and all these challenges altogether that I invite you to check there. And I thank you for your attention. I'm open for questions and I'm open for comments, and especially much more than that, I'm open for collaborations. Thank you very much, Fabio.
Thank you very much, Koe. All right, thanks a lot for this nice presentation. Do you have any comments here in the room? Online?
Hi, Cauê. André Ferlato here. Very, very nice
Andrew.
talk. It's a lecture about electrocatalysis, and I have two questions. One is more like a provocation. You mentioned in the beginning that PV is becoming very cheap. I mean, don't you think it's easier to just consider this green energy and work with electrocatalysis, forget about photocatalysis? You mentioned the techno analysis, and because if you work just with electrocatalysis, your portfolio of materials just extended very much, right? I mean, you don't have to think about absorbing the light.
Please.
Yeah, that's the provocation. Then I have a
okay. No, but you are right. You are right in the short term. I'm totally with you that the idea of a system, to be honest, maybe we are firing both sides of the situation, because the amount of electrical energy that has been produced by using solar light until now, currently we are below the demand of the system. Means that all the energy that has been produced by solar light can be used directly in the system as electrical energy. So, in other words, we could say that we don't need to use extra energy solar light till the moment. But if we are interested in doing some chemistry using solar light, this is the way that we are looking forward. This is the way to do this. You are right to say that we have a big portfolio for using some electrocatalysis if we do only electrocatalysis, but we still have the problem of stability of these catalysts. So the photocatalysis is more interesting. It is more interesting in the long term because we have more stable catalysts for doing that. Means that most the semiconductors, all the semiconductors, naturally they are not conducting in room temperature, means that they need some extra energy to be activated. And this extra energy will be the photovoltaic, the photo excitation, the radiation. So I understand that we are in a two-step situation. The first one is to make available a family of electrocatalysts, and this is why we are working with them. And the second one will be making available a family of photoelectrocatalysts. Catalysts. And again, in that system, photoelectrocatalysts, I understand that we probably will be working, first of all, in the photoanodic part, in photoanodes, and the second one in the photocathodes, Probably we are talking something like 20 years, 25 years developing things. But I understand that we need to do this in a kind of sequence, understanding that what the photocatalysts are doing is something that the electrocatalysts are not doing. But on the other hand, what the electrocatalysts are doing is something more will appear sooner than the photocatalysts in the market.
Okay, yeah, very nice. Yeah, I think that's the way. I mean, you can do parallel, but yeah, that's right. The other question is regarding this last catalyst, is this PHI. It is in the carbon nitride family. I've never heard of that. It's very interesting.
Yeah, this is a proposition that we learned from Professor Ivo Teixeira, who is working in this paper. We described this catalyst. This is a carbon nitride exfoliated with exfoliated by sodium. So we see here in the production of the catalyst, we use the mixture of the sodium chloride that can be replaced after the synthesis to put another metal there. For instance, the copper in that situation. The main advantage of the system is that we can put on isolated metals, making a kind of single atom catalyst over the surface of the carbonitride. This is more efficient for this kind of system, this kind of reaction.
Very nice. Is it easy to do? I mean,
pretty easy to do, really easy to do. Because this is only maceration of the system, and the thermal annealing, carbonization in conventional furnace.
Okay, thank you.
Thank you, Cauê. Any comments, questions? Ernesto.
Thank you. Thank you, Cauê, for this very nice talk. I have a curiosity. You told about the production of methane, green methane, and how this means concerning the electrical production from this methane. You talk about 3 million metric tons per day. This is the purpose. And how much electrical energy I can have with this amount of methane?
I think, Ernesto, we have a difference in that way. I think that the most important for us to understand is that the production of methane by biological means will be always more interesting in terms of energy expense. This is a biological process that has been produced by the nature using some bacteria that we don't know. We know a plethora of different bacteria. We know of several of them that can do this reaction. So the production of methane, I think, is more interesting through this kind of process, or like this one, instead of doing this in electrochemical by electrochemical means. But when we talk about the methanol production using this methane, coming back to this methane, we are talking to an electrical expense lower than the electrical demand for the oxygen. So in that case, I don't have numbers to give to you now because this is still in the infancy. But we believe that we can do in this system a more interesting alternative to produce all the other products of the reduction. In that case of CO2 reduction, or even the hydrogen production, but using a lower over potential to produce the same reaction. And in that case, again, we are transferring only 2 electrons. So the amount of electrons that we are transferring is lower than we have for the oxygen. So we expect that the amount of the electrical energy will be lower as well. And again, the product in that situation has some kind of industrial interest. Which we don't have for the oxygen. Then in that situation, I totally understand your question because I understand that the amount of electrical energy could be totally prohibitive in that situation. But this is a reaction that this is a commercial reaction actually. And you remember that the production of methanol till the moment is all the methanol is produced by the oxidation of methane to syngas. If we do this by electrochemical means, using some renewable methane instead of natural gas, we can have a more sustainable and more intelligent methanol in the end of the chain.
Thank you, Cauê. Okay, if you don't have any final comments or questions, I would like to thank you again, Cauê. Thank you very much for your talk.
Thank you again, Fabio. Thank you, everyone, all the audience.
Thank you very much. I'll thank all the speakers for this morning, the first session of our workshop. Thank you very much. Professor Ernesto as well, thank you again. Thanks for being here with us. And well, as a last word, tomorrow we have the second session here in the morning as well. And tomorrow we're going to have 2 online guests. And if you Cauê and Ernesto, if you have your time, also invited to join us here virtually. Okay, so
Will be
I'll wait
done.
for everyone tomorrow. Thank you very much again. Have a good day. Thanks, everyone.